Hello, my name's Andrew Norton. I'm in the School of Physical Sciences at the Open University. In this talk, I'm going to tell you about an astronomical detective story, namely the search for and identification of what became known as gamma-ray bursts. So let me share my slides. So here we go. Gamma-ray bursts, an astronomical detective story. First of all, then, what are gamma rays? Well, gamma rays are high energy electromagnetic radiation. We're familiar with visible light sitting here in the central parts of the electromagnetic spectrum at longer wavelengths or lower energies. We have infrared, microwaves, and radio waves. And then at shorter wavelengths, higher energies, we have first ultraviolet, then X-rays and gamma rays. So gamma rays are the very highest energy electromagnetic radiation. So they're indicative of very extreme events when we detect them elsewhere in the universe. Gamma ray bursts, then, the story goes back 50 years, really. In the late 1960s, there were a series of so-called Vela satellites, American military satellites, that were monitoring the Nuclear Test Ban Treaty. Now, they were looking down at the Earth for bursts of gamma rays coming from unauthorized nuclear weapons tests. But what they unexpectedly detected was bursts of gamma rays leaking in through the back of the satellites coming from outer space. Now, at the time, height of the Cold War, this was classified information, and it wasn't declassified until 1973, at which point it was realized that these bursts of gamma rays were coming from events out there in space. The first mission really designed to solve what these gamma ray bursts were was the Compton Gammaray Observatory, a NASA mission launched from the Space Shuttle in 1991. There's an image of it here on the end of the Space Shuttle arm as it was launched from the shuttle cargo bay. Now, there are various instruments on board the Compton Gammaray Observatory, but particular interest here is 8 detectors that were on the corners of the spacecraft. This whole spacecraft is about the size of a bus. And on the 8 corners were these modules called BATSI, the Burst and Transient Source Experiment. And they were specifically designed to search for gamma ray bursts because between them, they were monitoring the entire sky all the time. And this is what they found. Bursts of gamma rays coming from all over the sky. Here are just half a dozen individual gamma ray bursts. And what we're plotting here is essentially the number of gamma rays against time. And you can see that these bursts of gamma rays of various shapes. Some of them rise very steeply, just last for a few seconds and then disappear again. Some of them have a much more gradual decay with time. Some of them have multiple bursts coming from the same location. So there's clearly a variety of events happening here, but they're all spontaneous, unpredictable, and coming from random patches of the sky. So over the years that BATSI was operating on the Compton Gamma Ray Observatory, it recorded the positions of a couple of thousand gamma ray bursts. And here they are plotted on a map of the sky. The different colors just indicate the different energies of the gamma rays that were found. Now, broadly speaking, there were 4 possibilities for where gamma ray bursts originated. They could be very local, around the solar system, for instance. They could be originating within our galaxy, within the Milky Way. They could be somehow surrounding our galaxy, or they could be at vast so-called cosmological distances in other galaxies. And in fact, we can immediately rule out a couple of these possibilities just from this sky map of the BATSI gamma ray bursts. In this map, the plane of our galaxy, the Milky Way, would lie along the center of this image. Now, if this was a map in visible light, we would see the plane of the Milky Way across the center of this image. But here in these picture of the gamma ray bursts, there is no concentration of gamma ray bursts along the galactic plane. So that immediately tells us that gamma ray bursts can't be located within the galaxy. Otherwise, we'd see a concentration of them along the plane there. Another thing we can see is if we look at where our nearest neighbor galaxy would lie on this map, the Andromeda galaxy, that's over there shown by the position of the red circle, and we see no concentration of gamma ray bursts coming from the position on the sky of the Andromeda galaxy. Now that immediately tells us that gamma ray bursts cannot be around our galaxy either, because why should our galaxy be anything special? If they existed around our galaxy, they'd exist around the Andromeda galaxy too. So that leaves us already with just two possibilities. Either gamma ray bursts are very local, around the solar system maybe, or they're very distant. Now, you may already know the answer to this, but what I'm going to show you over the next few minutes is how that mystery was solved. The only information that we have about where gamma ray bursts come from and what they are is the electromagnetic radiation that we detect from them. At least that's the story at the beginning of this mystery. As well as that, we can tell when those photons arrived in a graph such as the ones I've just shown you. We can tell where on the sky they came from, and I'll say more about that in a moment. And we can look at the spectrum of the electromagnetic radiation. What's the energy, frequency, or wavelength of the photons that we're detecting? And if we put all that together, we can try and solve this mystery of what gamma ray bursts are. To tell what they are then, we need an accurate location on the sky. And it turns out that's quite difficult with gamma rays because we can't focus gamma rays like we can ordinary light with a mirror or a lens or something like that. The best way we've got of really locating gamma rays is using what's called a coded aperture mask, shown schematically here. We effectively form a shadow image of this, this thing that looks like a crossword puzzle, really, alternate opaque and transparent squares, which cast an image on a detector of the gamma rays. And we can use that shadow pattern to understand where on the sky the gamma rays are coming from. The trouble is, we can't locate the gamma rays very accurately with that technique. Typically, the precision on the sky with which we can locate the origin of gamma rays is about 1/2 a degree. Now, that's about the size of the full moon. 1/2 a degree is about 30 arc minutes, each arc minute being 60 arc seconds. Now, within a patch of sky 1/2 a degree across, the trouble is there are lots and lots of stars. If we go to really faint, deep exposures, looking at really faint stars and galaxies, we could find tens or hundreds of thousands of stars in a patch of sky that size. So that makes it very difficult to locate exactly where the gamma ray burst is coming from. The solution was provided by two X-ray astronomy satellites that were launched in the late 1990s, a European mission called Beto X and an American mission called Rossi Xte. What they were designed to do was to catch the fading X-ray afterglow of gamma ray bursts, because it was realized that although these gamma ray bursts had a very short burst of gamma rays, they were probably associated with a rather longer afterglow at slightly lower energies, namely in the X-ray part of the spectrum. And that's what these two missions were designed to detect. So here's Beto X shown schematically, and you can see one of the cameras on Beto X in the top right. That's one of these coded aperture mask instruments. You can see the little sort of crossword pattern imaging device on the end of this. And on board Beto X are a range of telescopes shown there colored in yellow and green and blue and so on in the diagram, each operating in a slightly different way, each able to locate the gamma rays and then the X-rays slightly more precisely on the sky. The Rossi Xte X-ray Timing Explorer similarly had a range of detectors on board, including an all-sky monitor shown there on this boom arm that scanned the whole sky and was able to pick up the gamma ray bursts and then turn to focus its X-ray detectors on the same patch of sky to locate the source, the afterglow, more precisely. And that's precisely what they did. What I'm going to show you is a case study of a particular gamma ray burst that was one of the ones that really solved this mystery finally. It goes by the name of GRB 980703. That means it was observed on the 3rd of July 1998. And in fact, the time when this was triggered on board BATSI was at 4 hours, 22 minutes, 45.22 seconds on that day. And you can see the structure of the gamma ray burst there. So on July the 3rd in 1998, this particular gamma ray burst was detected by BATSI on the Compton Gamma Ray Observatory, and Beto X and the Rossi X-ray Timing Explorer were then turned to look at that patch of sky to try and catch the fading X-ray afterglow. So here's a map of the sky. The circle is the uncertainty in the position as observed by Batsy. It's about 3 degrees across, so quite a big patch of sky in this case. Now, it turned out that there was a bonus here in that the Ulysses spacecraft out near the orbit of Jupiter, actually, was an interplanetary mission that happened to have on board its own gamma-ray detector. And that also picked up this gamma-ray burst. Because Ulysses is out by Jupiter, the time of arrival of the burst at Jupiter was slightly different to the time of arrival in the Earth's orbit, where Batsy detected it. And by kind of triangulation of that time of arrival, Ulysses was able to map out an arc on the sky where that burst came from. And that's shown here in the arc across this diagram. So where the arc intersects the big circle is likely where the gamma-ray burst came from. If we zoom in on that now, looking at what Beto X and the Rossi X-ray timing explorer saw, you can see that both XTE and Beto X detected the gamma-ray burst coming from just outside that big blue circle, the 3-degree circle of the Batsy detection. Now, that's not surprising that it was just outside the circle, because that was really only, if you like, a 90% confidence range where the burst was. And there's more area outside the circle than inside it. And as it happened, they got the position slightly wrong, but nonetheless, Beto X and XTE were able to pick up the gamma-ray burst from just outside the most likely position, but still within the arc of the Ulysses detection. And if you look at the inset portion, the purple diamond there is the localization of the X-ray afterglow from XTE, and the little red circle and the even smaller gray circle were the localizations from the Beto X instruments, which narrowed down the position even more. And drawn with a star inside the smallest circle, which is inside the diamond, you can see something marked there as optical transient. Because when optical telescopes turn to that same patch of sky, this is what they saw. The black circle here is the position from the Beto X so-called narrow field instrument. That localized down the X-ray afterglow to a radius of 50 arc seconds, much, much smaller than the original Batsy position. And sure enough, within that circle, there are rather fewer stars and galaxies. And one of those, shown here with the label RT/OT, that's radio transient and optical transient, was a new source of visible light and indeed radio waves, which had not been seen in this patch of sky before. So that optical transient, coincident with a radio transient, sitting within the narrow field location of the X-ray afterglow, which itself was very, very close to the rather poorly determined position of the gamma-ray burst, seems to be the source then of this gamma-ray burst itself. And when one of the largest telescopes on Earth, the Keck telescope, was pointed then to look at this optical transient, only on the 6th of July, that's only 3 days after the gamma-ray burst itself went off, it was able to measure the spectrum of that source of light. Now, what they saw in this spectrum was a hugely redshifted set of spectral lines. Now, redshifted spectral lines have a very familiar interpretation. We interpret them as due to the expansion of space. The further away we look, the faster objects appear to be moving, because space is expanding faster the further away we look. And by measuring the redshift of these spectral lines observed in the optical afterglow of this gamma-ray burst, this was measured to have a redshift of 0.966. Now, converting that to a distance away or a time in the past at which this object was seen, this must be an object which is 10 billion light years away. The light from this object was emitted when the universe was only 6 billion years old. That's about 7.5 billion years ago. So there then, as a result of this multi-wavelength observational follow-up in gamma rays, in X-rays, in optical light, was finally able to pinpoint the source of this gamma ray burst as being an object in the very distant universe. So where do gamma ray bursts originate? They're not around the solar system. They're not something very local. They really are at cosmological distances. So around this time, and indeed even before this was finalized, astronomers had come up with models for how gamma ray bursts operate. And this so-called fireball model was the commonly accepted method of how they work. There is some central engine, we'll come to exactly what that is in a moment, emitting jets perpendicular to each other, sorry, parallel to each other, one behind, if you like, one towards us. And that jet is accelerating into some gaseous medium within the environment that the gamma ray burst sits. And as that flow decelerates and is slowed down by crashing into that material, so collisions within that flow give rise to first X-rays and then optical and radio waves and so on as the flow decelerates. The jets themselves are pretty narrow at opening angle of perhaps only a few degrees, but importantly, the speed at which these jets propel out into the environment are 99.99% of the speed of light or more. So they're very, very energetic processes. But as Compton Gamma Ray Observatory and other observatories detected more and more gamma ray bursts, it was soon realized there are actually two different sorts of gamma ray bursts. Shown here on the left is a histogram of the number of bursts against their duration, and on the right is a scatter plot of what's called the hardness ratio, which measures the spectrum of gamma rays, how high or low energy the gamma rays are, again against the burst duration. And it's seen that there are likely two populations here. There are some short, high energy bursts and another population of longer, lower energy bursts. And pretty soon people came up with models for what these could be. The short, high energy bursts, of which there are rather fewer, these are believed to be due to mergers of pairs of neutron stars, whereas the longer, lower energy bursts are in some way related to supernovae and were nicknamed hypernovae. So let me just show you a couple of animations that illustrate that. So here's the idea of a pair of neutron stars. These are the remnant cores of massive stars that are orbiting around each other. And as they spiral together, losing energy, they will eventually collide and merge, releasing this burst of gamma rays that we observe as the so-called gamma ray burst. Now, that was only a model at this time. What I'll show you shortly is how this was finally proved to be the case only in the last few years. The second type of gamma ray burst then, the much longer duration, lower energy type, believed to be related to supernovae. Now, supernovae occur when a massive star reaches the end of its life, runs out of nuclear fuel in its core and collapses, then rebounds, giving this massive explosion. So this type of gamma ray burst, referred to as hypernovae, are believed to be due to very, very massive stars, maybe 100 or more times the mass of the sun, that existed only in the very early universe. So we now see at very great distances. And when those very massive stars died, they produced this kind of hypernova explosion that we recognize as the longer duration gamma ray burst. So in the past decade, or 15, 16 years or so, the mission which has been studying gamma ray bursts most successfully is the SWIFT satellite. It was unique in that it was on a single observatory. It had both gamma ray telescopes and an X-ray telescope and optical telescopes. So it could do this follow-up, if you like, all on its own. It's been operating since it was launched in 2004, and it's been remarkably successful. I'll show you a little video here of the first 500 gamma ray bursts that were detected by SWIFT. You can see some highlights. The first burst with an afterglow detected, gamma ray burst 12.7 billion light years away. Gamma ray burst including X-rays from a supernova shockwave, and many other. Gamma ray bursts occurring randomly all over the sky. No two recurring in the same location, but scattered all across the sky. And many of these were followed up with multi-wavelength observations. And as these observations were made, it confirmed this picture that we have, that gamma ray bursts occur in the distant universe, hypernovae type, the very massive stars that are exploding at the end of their lives, are in the very, very distant universe. The shorter, higher energy gamma ray bursts associated, we think, with merging neutron stars, many of those were actually rather nearby. So how was it finally proven then that gamma ray bursts really were associated with merging neutron stars? For this, we turn to gravitational wave astronomy. Now, this is something that's really only been possible in the last few years. Here's an image of the Virgo gravitational wave detector in northern Italy. And on the right is the principle of how it works. So we have two very long laser beams, which, several kilometers long at right angles to each other. The idea is that as a gravitational wave passes through our detector, so the relative lengths of the two beams, the two arms of the detector, change as the gravitational wave passes through. And if we combine those two laser beams to form an interference pattern, as their length changes, so the interference pattern will change, and we can then detect the passage of a gravitational wave. Now, that sounds easy, but the relative change in length that we're talking about is 1 part in 10 to the power 21. That's like considering the distance from here to the nearest star changing by the width of a human hair. So it's a tiny, 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 unbelievably tiny change in length. But nonetheless, that's the sensitivity that Virgo here in Italy and two American detectors called LIGO in the United States are able to detect. And what they detected in the last few years was then direct evidence of gravitational waves. And here's the very first gravitational wave detection that was made in September 2015. The graphs there are the signals of the gravitational wave, and plotted at the bottom is a sort of graphic representation of how the frequency of gravitational waves changes with time. And you can see this characteristic concave shape in the graph. And this signal then was determined to be from the merger of two black holes. Two black holes, each of weighing several tens of times the mass of the sun, which merged together, converted a significant amount of that mass into gravitational energy and emitted it as gravitational waves. Over the next couple of years, several more of these gravitational wave events were detected. And here's a plot of the first 11 that were detected. 10 of these are rather similar. They're due to pairs of merging black holes. But the 11th one, shown in the bottom right, as you can see, has a slightly different duration and intensity. And this one, GW 170817, was believed to be the first gravitational wave detection from a binary neutron star merger. And let me try and show you a little movie of this. So what we're showing there is the gravitational wave detection with this characteristic chirp. And then literally just 1.7 seconds later, there was a detection in gamma rays, there it is, from the Fermi gamma ray satellite. So there we have an almost simultaneous detection then of gravitational waves and of electromagnetic radiation. A gamma ray burst was associated with the gravitational wave detection. And sure enough, when the source of that was followed up here in an optical image of the galaxy NGC 4993, there you can see the event that triggered both the gravitational wave event, GW 170817, and the gamma ray burst, GRB 170817A. In fact, there was a second gamma ray burst detected from elsewhere on the sky in the same day. That's why this got the letter A attached to it. But both of these events then, in electromagnetic waves and gravitational waves, were due to the same event. This then was the confirmation that short gamma ray bursts are indeed associated with the merger of a pair of neutron stars. And that then is the solution to the mystery of gamma ray bursts. Gamma ray bursts, or at least the short ones, are due to the merger of neutron stars. And incidentally, merging neutron stars are believed to be the source of all the gold and platinum in the universe. So if you're wearing any jewelry, got my wedding ring there, all of the gold atoms in that jewelry were formed in events like this that occurred way before the Earth was born, many billions of years ago. So I'll stop my slides there. I hope you enjoyed this astronomical detective story, and please watch some more of these lectures at another time.